Hello, everyone, and welcome to Spectral Geometry in the Clouds. It is our great pleasure today to listen to Luc Hillairet from Orléans, who is going to tell us about spectral tools for geometric degeneration. As usual, don't hesitate to ask questions in the chat or by unmuting yourself. And yeah, Luc, the floor is yours.
Thanks, Laura, and thanks to the organizers for inviting me to give this talk. So I will start by presenting a very general question. So this is a spectral geometry seminar, so I assume that this is one of the questions that everybody studies. So we have a set M of parameters and X a compact manifold, and suppose we have Gm, a Riemannian metric on X that depends on M. And so what we want is study the spectrum of X equipped with this metric as a function on this set M. So this means this can mean different things. So either we can look at individual eigenvalues or functions of the spectrum. So like, for instance, the heat trace or the spectral determinant. And then we can look at variations of this function inside M or the behavior at the boundary of M. And so there are many generalizations of this question, like domains or Schrödinger operators, and so there are many things that can be studied in this general framework. And so I wanted to give a disclaimer. So I will not speak on optimization problems and nor on variations in a fixed conformal class. I will be more interested in variations where we have only a finite number of parameters that are at play. And I will focus on the behavior at the boundary, that is degenerating families. And so first, and most of what I will discuss today is based on a joint work with Chris Judge that started some time ago. So some examples that are well known or well studied that gave us some inspiration and motivations. So the first one is something that has many names in the literature. So one is shrinking manifolds or thin strips, so that have been studied, for instance, by Rubinstein, Schatzman, Cushman-Zeng, Exner-Post, Friedlander, Solombiak, and many other people. So it's for instance, what you see on the left is a domain that is obtained by scaling vertically a fixed profile. And on the right is maybe some graph that is thickened in R2. And you want to study the behavior of the spectrum when t goes to 0. So the other thing that we were interested in is simple shapes. So simple shapes either in Euclidean, hyperbolic, or spherical space. So simple shapes like polygons, triangles, or ellipses. And so maybe we want to study what happens to the spectrum when the triangle degenerates onto a segment, or the circle degenerates into a family of ellipses that also collapse onto a segment, or in the hyperbolic plane, like for instance, a triangle, a hyperbolic triangle with one cusp, and that degenerates when t goes to 0. And I mentioned also this stadium billiard, which has been studied by Hassel, and that will come up a bit later in the talk, where here you move the length of the rectangular part of the billiard. So another kind of motivation is for hyperbolic surfaces. So where you have tension-Nielsen coordinates. So for each geodesic, you have a length and a twist parameters. And then you have several degeneration scenarios, and like that mostly correspond to pinching of geodesic, and that has been studied by Volpert. And actually, when we started working on these questions with Chris, one motivation was that of translation surfaces. So translation surfaces is you take a Riemann surface and a holomorphic one form, and then you equip the surface with a flat metric with cone points that is given by the modulus square of the holomorphic one form. And so there has been a great work by Kokotov and Korokin, where they compute the spectral determinant for this flat metric with cone points using, so they give an exact formula using objects from the complex geometry of the surface. And we would like to understand how these metrics can degenerate at the boundary of moduli space. And so this means either that cone points coalesce, or you can also think of cylinders that become small or long or very long, depending on the normalization. So here you have an example of such a translation surface, which is obtained by identifying the horizontal and vertical sides of the same color. And so what you see is, for instance, the two cylinders. So one cylinder that is of length 2 and one cylinder which is of length 1. And actually this surface is a genus 2 surface with one cone point. So the question I was asking is very general, and I want to be slightly more precise in this slide. So I will consider an eigenvalue problem on a fixed domain D that depends on a parameter T. So my parameter will always be one-dimensional in order to use analytic perturbation theory. And so the eigenvalue problem is written like that. So ut is in the form domain, and for all v in the form domain, you have qt of utv is et nt of utv. So qt is the quadratic form on the domain D, and nt is a family of scalar products that gives equivalent Hilbert norms on my ambient Hilbert space. And so when you have such a problem, you can look at it in two different ways. So first, you can look at the ordered eigenvalue problem. So that means that for any k, you study the behavior of the kth eigenvalue when t goes to 0, for instance. And then you can also look at the analytic eigenbranches problem. So if you assume that qt and nt depend analytically on the parameter t, then the spectrum consists in analytic functions. So there are a countable number of analytic functions, et, and you have another index n, which I don't write, and so that describes exactly the spectrum. And you also have analyticity for the corresponding eigenvector. And so the remark here is that analyticity is good to obtain generic simplicity results, for instance, because if you have two branches, two analytic branches, either they always coincide or they coincide only for countably many values of the parameter. So there are these two problems, and the first thing I want to show is that these two problems are really different. And this is clearly seen on this example. So if you imagine a cylinder of length 1 and width t, and say, for instance, a Neumann boundary condition on the red boundary, then you look at the quadratic form that is written here. So you have the this is the usual Euclidean Dirichlet energy form, except that the x direction is scaled by t squared. So this accounts for the width t of the cylinders, and I have renormalized so that the eigenbranches go to 0 at finite limits and don't go to infinity. And then so here the ambient Hilbert norm does not depend on t. And the domain is H1 to account for Neumann boundary conditions. So here you can count, you can write explicitly the spectrum, and so the spectrum of the corresponding operator delta t, which are the m squared t squared plus 4n squared times pi squared, and when n and n are non-negative. And so I've sketched this picture on the right. And so you see you have these thresholds that are the 4n squared pi squared. And for each threshold, you have infinitely many branches that go down to it like m squared t squared. And so what it tells you is that for any k, the k's eigenvalue is given by one of these black eigenbranches, and it's asymptotic to t squared times the k's eigenvalue of the interval. And for this, so this you obtain by putting n equals 0, because any other eigenbranch will converge to a multiple of pi squared. And so so that's for the case, that's for the ordered eigenvalue problem. And for the eigenbranches, what you see is that any analytic eigenbranch has a limit when t goes to 0, and the possible limits are quantized. So it must be one of the thresholds for n squared pi squared. And if you're interested in multiplicity results, what you also see is that the black eigenbranches, so the ones that go to 0, they are simple because they correspond to the transversal mode, that is constant. But any other eigenbranch is of multiplicity 2. I mean, generically, because there can be crossing, so it can have multiplicity higher than 2, but generically it will be of multiplicity 2. And so if in your argument you don't see you study only the ordered eigenvalue, then you don't see any multiplicity in the limit, whereas there is always multiplicity. So this is one problem that we will face later when studying multiplicity. So the other difference between ordered eigenvalues and analytic eigenbranches can be seen when you study a semiclassical Schrödinger operator on the line. So say so I've written the quadratic form associated with such an operator. So V is my potential. So you can imagine that it's smooth and say with a one minimum and going to infinity, so that you have nice discrete spectrum. And so now the standard semiclassical techniques, such as the WKB expansions or the harmonic approximation for the bottom of the well or any quasi-mode construction, actually these are linked with the ordered eigenvalue question. And these are usually what people do in the semiclassical analysis of such an operator. And so if you want to study analytic eigenbranches of this Schrödinger operator, what you do is you use this Feynman-Hellman formula that gives you the derivative of the analytic eigenbranch of QH with respect to the NH, which I haven't written because it does not depend on H. And so so this formula tells you that the derivative of the eigenbranch is given by the derivative of the quadratic form Q dot evaluated at QH minus EH n dot evaluated at QH. So this is a very general formula that we'll use several times in any time actually we want to study analytic eigenbranches. And so in this example, what you obtain is that the derivative is 2 over h times this integral of h raised to u prime square that you can rewrite like the integral of e minus v of x uh squared dx. And so you immediately see that it is positive. And because it is positive, it implies that EH has a limit when H goes to 0. And so so that is this function, the derivative of EH is integrable. And because you have this 1 over h in front, it tells you that what's behind the parenthesis must go to 0 along a subsequence. And so that means that so if you look at the expression on the right, it means that has to concentrate on the points where v of x is equal to E0. And so, I've drawn a picture with your potential V, and so some non-critical energy E0, and so you have these 2 points which are classically called turning points. And so if E0 is a limit of an analytic eigenbranch, then you must be able to construct a subsequent UH that concentrate on this set on the turning points. And so, as is well known in the semi-classical analysis questions, is that you can study these questions of concentration or non-concentration by looking in the phase space. And so in the phase space, you have this energy surface, and so you want to find concentration on the red dots. But you also know that there are these things called semi-classical measures that tells you that any limit of such an expression has to be invariant, is associated with a measure on the energy surface that is invariant. And here it tells you that it's not possible to concentrate on these 2 points. And so using semi-classical measures, you see that the only possible limits E0 are necessarily critical points of the potential V. So, the situation is like this. So I've drawn the spectrum of my Schrödinger operator, and I've drawn the eigenbranches. So the eigenbranches go down to the minimum of the potential, if I imagine that I only have one minimum, and the usual semi-classical question studies what happens in a non-critical energy window. And in this non-critical energy window, what happens is that you have all these branches that cross with a very steep slope. And so what is interesting in this example is that you immediately see that there is a relation between the variation of the eigenvalue branches and the concentration of eigenfunctions. And so this relation is one ingredient of Hassel's proof that the stadium is generically non-QE. And what's also interesting is that although so what do we learn from these two examples is first that the study of ordered eigenvalues and the study of analytic eigenbranches are fundamentally 2 different problems. But although there are 2 different problems, you can use tools from one side to study the other one using this Feynman-Hellman formula. And so, and that's because determining the possible limits of eigenbranches is related to semi-classical concentration properties at the energy E0. And so, and the last thing you learn from these 2 examples is that if you can use separation of variables or one-dimensional Schrödinger operators, then it helps. Statement that you can verify many times. So now I will look at more general domains with this in mind, and I will take and the first thing I want to study is these collapsing domains. So I take L. So I've written a nice function because I don't want to be too precise, but imagine, for instance, smooth on this interval AB, and that is positive on AB. And then you look at the strip between that has such that y is less than L of x. And this qt of u, which is the same expression as before, which corresponds to shrinking the domain up to a renormalization. And now you choose this domain D. So it's very important. It's very important in order to apply analytic perturbation theories that the domain is fixed. So anytime you have you want to study the Laplace operator, for instance, on a varying family of domains, then you have to trade a fixed operator on a varying domain with a varying operator on a fixed domain. And so that's what we have done here. So that's why the T is in the operator and not in the domain. And so now you can encode different boundary conditions. So and I've drawn in at the bottom three different kind of domains. So the first one is the family of triangles as before. The second one is the family of ellipses, and the third one is where you have where L is positive also at A and B. And so on this, you see that there are two kinds of boundary conditions. So there are the boundary conditions on the red side, which I will call the transverse boundary condition. And if there are vertical sides, then there are these green boundary conditions. And so you can choose any Dirichlet or Neumann on these sides. And so the other eigenvalue problem is actually well studied. And so so I've written here for the Dirichlet case, but we'll see that you can do things also in the other cases, the other boundary conditions. So the observation is that if you take functions that are of the form v of x times sine pi y over L of x, this gives you reasonable quasi-modes. And so that the first eigenvalues of the corresponding operator are approximated using the 1D Schrödinger operator that has potential pi squared over L squared. So this is called sometimes the effective operator. And so so there are a number of comments here. Is that so the sign actually is the fact corresponds to the fact that I have chosen Dirichlet boundary condition on the transverse on the red side. So if you choose Neumann or mixed Dirichlet Neumann, you will have to change this sign with the first eigenvalue of the corresponding problem. And what you see also is that the eigenfunction will concentrate where L is the largest possible. And you can have a two terms asymptotic expansion using Friedlander and Solomiak work. And that gives you an answer for any L that has a unique maximum with a local shape of the form x to the alpha, actually x plus to the alpha and x minus to the alpha. So the same strategy applies for transverse Dirichlet-Neumann boundary condition. If you have full Neumann, it's simpler if L does not vanish at the sides, and I will see later a related question. So that's for the ordered eigenvalue. But what do we know about analytic eigenbranches?
Can I ask something here, Luc?
Yes.
So you made this comment that for the Neumann boundary condition, it's easier if L is positive everywhere. Yes. Is there a good heuristic reason to see why this should be easier?
Yes, it's because the potential is k squared pi squared divided by L squared, and so when k is 0, this is 0, and so you have to do something else.
Okay, yeah, okay, that makes sense. Thanks.
And so this is one theorem that we've proved with Chris some time ago. And so if you assume that L is smooth and increasing on AB, and you take Dirichlet or Dirichlet-Neumann boundary condition, transverse boundary condition, then first any analytic eigenbranch ET converges when T goes to 0. And you can say something about the possible limits. So in the Dirichlet case, the possible limit is of the form k squared pi squared, which are the eigenvalues of the interval with Dirichlet boundary condition. And in the Dirichlet-Neumann, it's k plus 1/2 squared pi squared, which are the eigenvalues where you have one end Dirichlet and one end Neumann. And so I will sketch a proof. I will give more details on this proof, but I just want to give you an outline here that it uses an asymptotic separation of variables. So we will try to use 1D operators and then use Feynman-Hellman formula and the semiclassical concentration estimate. So how does it work? So this asymptotic separation of variables is quite well known. It's also found in the literature as the adiabatic approximation. So I will write it in the Dirichlet case. So if you want to write it in the Dirichlet-Neumann, you have to change the sign for the eigenvalues of the interval with Dirichlet-Neumann boundary condition. And so if you make, so what you do is you make a Fourier decomposition at fixed, Fourier decomposition in y at fixed x. So of course this works well with the derivation with respect to y, but if you try to differentiate with respect to x, then you will have two terms. And so you call the first one big D of u, and then the second term you see that it's something that is that can be written y L prime over L times dy of u. And so this y L prime over L, so y over L is always between 0 and 1. And so you assume that this L prime is bounded. And so when you do that, if you look at the norm, the Hilbert norm of T dx u, then you have you gain an extra T on the cross terms. And so what you have is that T dx u squared is like the norm of T du squared plus a big O of T times a quadratic form that you call A of T. And so the quadratic form you're interested in, Qt, is a big O of T perturbation of the quadratic form A of T that is defined like T squared du squared plus dyu squared. And if you look at the expression for dyu and for du, you see that this quadratic form appears as a sum of one-dimensional quadratic forms that correspond to Schrödinger operators. And so the spectrum of AT can be analyzed by separation of variables. And what you obtain is that it is the union of the spectra of the following Schrödinger operators. So minus T squared U plus with potential K squared pi squared divided by L squared.
There is a question in chat right now, as Daniel Grisa asking if you normalize the maximum of L to be 1.
Not necessarily. Not here. Yes. So
I just thought because
for the statement of the theorem, yes.
Yeah. Okay, that's what I meant. Yeah.
Yes. Yes.
Yeah. Thanks.
Yes. Otherwise, you will have yes. So it's normalized. So the maximum is 1. So and now now you want to see these possible limits pop up. And so I told you that this comes from a semiclassical concentration. And so we will use Feynman-Hellman formula. So that gives it gives us that the derivative of the eigenbranch is q dot at ut. And so if you look at the eigenbranches of A, you will have A dot at ut. And so the difference is bounded by qt. And so again, you know that so this tells you that the function A dot of ut is integrable when t goes to 0. Because q dot of ut is, and so that's because so you first prove that E of t converges to E0, and then you study the possible limits. So and so this gives you this integrability criterion that the limit of h times A dot of uh is equal to 0, and so now you have a subsequence along which you have this quantity, and what do you know about UH? UH is an exact eigenvalue of Q, and so because it is an exact eigenvalue of Q, and A and Q are O of t, one of the other, it tells you that it's a quasi-mode of A of order 1 at energy E0. And so now you work and you prove that if you take if you suppose that E0 is bigger than this threshold, k squared pi squared, and you take a quasi-mode of order 1, then you find a positive kappa such that h times a dot of UH is bounded below by kappa times the norm of UH. And so that is the contradiction you were looking for, and that tells you that E0 has to be one of these thresholds. And so again, it's a bit surprising at first that in order to study these analytic eigenbranches question, you end up using semi-classical concentration, but that's how it works. And so let me just remark here that so the quasi-mode you obtain is big O of 1, order 1. And so if you had small o of order 1, then you could use semi-classical measures and the invariance of the semi-classical measures to prove that you have such a statement exactly that as we did in the first place with exact eigenvalues. And so here you have to work a bit in order to improve from small o of 1 quasimodes to big O of 1 quasimodes. And there we really use that we are dealing with 1D Schrödinger operators where we can use, for instance, area approximations near the turning point and things like that. And so, so once you have that, we use this to prove that the generic triangle, Euclidean triangle, has a simple spectrum. And so, so this is how we prove this. So we make a contradiction argument. So using analytic eigenbranches, by contradiction, we suppose that there is an analytic eigenbranch that is of multiplicity 2. And then we prove that along such an analytic eigenbranch, then ET has to converge to one of these thresholds, k squared pi squared. And we use again the Feynman-Hellman formula, but in the other way around, to say that so now we have the higher modes, so the modes that are bigger than k. So on these modes, because UT is a quasi-mode of AT, the corresponding part of UT has to be very small on this mode, on these higher modes. And on the smaller modes, we cannot directly conclude that it is small, but we can use the Feynman-Hellman formula the other way around, and it gives us that it actually has to be small too, so that UT essentially lives on mod k. But on mod k, it is good because on mod k, we know that the eigenbranches of AT separate at order t to the 2/3. So that's reminiscent of the fact that the profile function L, it has absolute value singularity for the bottom of the potential. And then here, area approximations tells you that the eigenvalues are of order t to the 2/3. And let me, so the picture is like that. So you have this, the spectrum of AT, which are all these branches, the blacks, the greens, and the blue. And now you have this eigenbranch of QT, ET that converge to this threshold. And so, so when you compare to the green eigenvalue, to the green eigenbranch, then here it is good because if you have a simple spectrum such that the distance between two consecutive eigenvalues is of order t to the 2/3, then any perturbation that is smaller than that, so in particular a perturbation of order t, you will still have simplicity of the spectrum. And I just want to mention that it's fortunate that we can separate the lower modes, because the lower modes, if we could not say that the eigenfunction has small mass on the lower modes, then we would have a problem, because if you compare this red line compared to the black lines, which are the lower modes, then the separation between two black lines is of order t, because for the Schrödinger operator that correspond to the black lines, E0 is a non-critical value of the potential, and there the eigenvalues are separated at order t. And so we really need to be able to say that almost all the mass of Qt is on the mode where the separation between eigenvalues of AT are much bigger than t. So this is some work in progress with Chris, where we prove that the generic ellipse are also simple. And so it's actually a bit simpler, because so we have this Bourget's hypothesis, which tells us that the spectrum of the half disk is simple. So it's a strange statement. The first one you see that is that almost, although the disk is the most symmetric object you can think of, the spectrum is only of multiplicity 2. And so now we must refine a bit what we did before, because L prime blows up, and so we don't have this asymptotic separation of variables everywhere. But for Dirichlet, if you have one side at least that is Dirichlet, then you can first prove an estimate that tells you that the corresponding eigenfunctions will have small mass near the place where L prime blows up, and so you can separate, you can get rid of this part and construct your quasi mode that will give you the contradiction in the end. And so what you know now is that if you take the spectrum of the ellipse, then you separate it in two half disks, half ellipse. So the one where you have Dirichlet boundary condition on both sides, and the one where you have Dirichlet. So I mixed. I made a mistake. So the Dirichlet is on the curved side, and on the curved side, and the Neumann is on the flat side. And so what you know is that if you took at these two spectral problems, so each spectral problem is simple at t equal 1, has simple spectrum at t equal 1, so that's Bourget. And now when t goes to 0, then you go to the limits that we saw before, which are different if you have Dirichlet boundary condition or if you have Dirichlet-Neumann. And so the fact that, so now imagine that you have an eigenvalue, an eigenbranch that has multiplicity 2. So it cannot be on one of the, it cannot be neither on the left side nor on the right side. And so it has to be an eigenvalue both of the right and of the left side, but that's not possible because they have different limits when t goes to 0. And so that gives a generic simplicity of ellipses when you have a Dirichlet boundary condition. And so the case where you have Neumann boundary condition is harder. And okay, I don't claim it right now. So that was my first kind of degeneration. And now I want to study a second one, which, okay, I called it grafting, but again, there are many names in the literature for this kind of thing. So you can see it either by you start from a graph, and now you will construct a surface by replacing each edge by a Euclidean cylinder and each vertex by a compatible junction. So these junctions, so for instance, on the right side, so you see that I have this graph with one loop and one segment. So I have two junctions because I have two vertices. So one is just this end on the right with a boundary component, which is a cylinder, and I have this junction. It's like plumbing. So you have these plumbing parts, and on these plumbing parts, plumbing junctions, you glue cylinders, and you glue cylinders that becomes longer and longer. So like L1 over T and L2 over T, and you have another parameter, which is the width of the cylinder. So that's sigma 1 and sigma 2. And so that's when you start from the graph. And so in Teichmüller theory, there's something which is called grafting, which is related. So there you start from a hyperbolic surface, you isolate a geodesic, and now you cut along this geodesic, you insert back a flat cylinder, and you look at how the conformal structure evolves when the length of the cylinder that you have inserted grows to infinity. And so that's the second kind of degeneration I want to consider. And so again, the ordered eigenvalues, there's a large literature on the question. So I think the first, so you have something like Rubinstein. So I've given a few names, but there are many others. So Rubinstein, Scheitzman, Cushman, Zeng, Exner, Potts, Greiser wrote a nice survey, and so what you see is that the kth eigenvalues behave like t square lambda k, where lambda k is the kth eigenvalue of a Schrödinger operator on the limiting quantum graph with Kirchhoff vertex condition. So the simplest case is where all the sigmas are the same. So if all the sigmas are the same, then it's just a standard quantum graph Laplace operator that you obtain. And let me just explain how you see the Kirchhoff vertex condition pop up. So you can write a compactness argument. So if you consider a sequence ET UT such that ET is bounded above by a constant time t squared. So I have renormalized so that that's why this t squared comes into play, because so it's this problem is the same up to scaling, like fixing the graph and putting around the edges cylinders of size t. So if you have cylinders of width t and fixed length, then the spectrum converges to the spectrum of the graph. But now I have rescaled by t squared, and so that's why my t squared is popping up everywhere. And so you extract a subsequence like that. Then you look in each piece. So in the cylinders, you perform an exact Fourier decomposition, and so you see that in this exact decomposition, because you're going to zero because of this t squares, because you're going to zero, so it tells you that you have to concentrate only on the zeroth mode, which are the functions that does not depend on y, and so on each edge you obtain a function that is a function that depends only on x. And in the junctions, it's the same story. So you have energy that goes to zero, so you have to go to a constant, and because you have and so in the end, extracting a subsequence, you obtain a function that has a constant value on each vertex. And so if you look at the quadratic form formalism and you restrict to the H1 function that that are continuous on the graph, then it immediately implies that it is Kirchhoff boundary condition. And so that's for ordered eigenvalues. And so I have a student, Franchel Gatz, who studied the analytic eigenbranches in his PhD thesis from for these kind of problems. And so what he proves is that any analytic eigenbranch converge. First, any analytic eigenbranch converge when t goes to 0. And then that the only possible limits are the transversal eigenvalues. So these are these 4k squared pi squared divided by sigma I squared. So these are the thresholds we were discussing before. But there are there is another possibility, is that for each junction, you can imagine the non-compact surface that is obtained by gluing an infinite cylinder on each boundary component of the good width. And if this non-compact manifold, non-compact surface has embedded eigenvalue, then it is also a possible limit of the analytic eigenbranch. And so the proof consists in carefully using Feynman-Hellman formula to estimate the mass in the cylinder. So actually what you prove is that if the limit, you want to prove that if the limit is not one of these transversal thresholds, then it has to be an embedded eigenvalue of one of the extended junctions. And so using Feynman-Hellman, you prove that the mass in the cylinder has to go to 0 if the limit is not one of the thresholds. And so because the mass in the cylinders has to go to 0 and you have a finite number of junctions, then it has to concentrate in at least one junction, and then you can look at what you have and see that you construct actually a quasi-mode for an eigenvalue, an embedded eigenvalue. So now I will. So I've almost. This is my last slide, so I'm a bit. And so I want to finish with an open question. And so the question is the following. So is it really possible for an eigenbranch to converge towards the highest thresholds? So of course it is possible to converge to the lowest threshold. And the question is whether it's possible to converge to something with k which is not 0. And so, of course, if you have separation of variables, exact separation of variables, then you know that it is possible. So we saw it for this 80 quadratic form that we had before. But now, if you perturb this picture, then you know that the crossings usually becomes a voided crossing. And so I've drawn this picture where you have this black curve that go down to the bottom, the lowest threshold, and you have these two green curves that converge to a higher threshold. And so you imagine that you have this red curve, which is supposed to be an eigenvalue of Qt. So Qt is the quadratic form that you want to study, and so it has to be very close to an eigenbranch anytime. And so first it is close to this green eigenbranch. And then it approaches a crossing, and when it approaches a crossing, it jumps from the green to the black, and then when it approaches the other crossing, it jumps again from the black to the green, and because for the black eigenbranch, because you're near a non-critical energy level, the derivative of the black line is very high. And so this red eigenbranch, when it's close to the black eigenbranch, it has a very high derivative. And so if you're able to, and if you imagine that this red line converges to the green threshold, so it will keep on crossing these black lines because there are infinite number of eigenbranches that go down to the lowest threshold. And anytime it crosses such one of these black lines, it will interact with the lower modes and it will have a high derivative. And what happens is that what can happen is that anytime if it has enough high derivatives on some intervals, you can sum up all these derivatives and eventually obtain a contradiction with the fact that the red eigenbranch was going to the green thresholds. And so that's the idea we used with Chris to study embedded eigenvalues in hyperbolic triangles. And I will stop now.
Thank you very much, Luc, for this very nice talk. We now have time for questions. So please, if you have a question, just unmute yourself or write it in the chat.
Okay, it's Yves. I have a question. In fact, several questions, but let's say one. If you fix, in your example with triangles or ellipses, if you fix K, do you know if there is a finite number of triangles for which, or ellipses, for which lambda K is degenerate? I guess it's true, but at least for triangles, but for ellipses, I don't know that. Because you are now.
No, basically, we don't know anything about. We suppose it's true, but we don't know. We don't know it.
Okay,
we don't know how to prove it.
You can look at the moduli space, which is two-dimensional, and you go to infinity, and you have.
Yes, but the problem is you could have a curve inside the moduli space where you have a multiplicity.
Ah, seems to be very not.
Yes, but that's actually I think you can prove that you cannot have a curve that goes to the boundary on which you have multiplicities. That's what we prove.
Okay.
Basically, more or less.
Okay. And the same for ellipses, I guess.
Yes.
Okay. Okay, but it should be very strange, but okay.
Colin, you had another question?
Yeah. What do you know something about the case of hyperbolic surfaces of fixed topology?
No, so these two questions are the two of the questions we tried. No, so the problem with no, we don't know how to prove that the generic hyperbolic surface has a simple spectrum. We think it's true, but we don't know how to prove it, and the reason why it's so for instance, if you look at the pinching degeneration, so you pinch, and so you have asymptotic separation of variables in the color, but the mass of the rest is very big.
Okay.
So you cannot.
In general, you have a continuous spectrum which is of multiplicity,
yes,
at least two, because there are several cusps.
Yes, but the continuous spectrum is not. Okay, it's not too much a problem.
I'm not sure, but
yeah.
Okay.
So we have tools to deal with the continuous spectrum in this setting.
Okay. Thank you.
Does anyone else have questions or comments?
Yeah, I would have a question. So In the examples that you presented today, it was all for self-adjoint problems, right? But all these ideas from analytic descriptions of these eigenbranches could presumably work for extensions in non-self-adjoint directions. Do you know if the methods you develop work also for non-self-adjoint operators and studying these analytic branches?
It's okay. So non-self-adjoint operators it's a different world. So even for analytic eigenbranches, so there are, because you can have okay, so you can have Jordan blocks or things like that, and so it's much harder for me. And so you can do things, and but I so here we really use the fact that it's self-adjoint, and so it's but you can use these techniques to study, for instance, resonances in manifolds with cylindrical ends. So, for instance, because there you can so that's what I was saying. I was thinking when saying that we have tools to deal with the essential spectrum. So in this case, you know the essential spectrum, and so if you want to study embedded eigenvalues, then you can make a finite rank perturbation, and so and then you end up studying a self-adjoint operator and your embedded and then you can use these kind of techniques. So, but for real non-self-adjoint, I don't know. You have to be careful.
Mm-hmm. Yeah, no, I mean, I know it's much more difficult, but I was wondering if you were using strongly self-adjointness, and it seems that it is the case.
Yes.
Yeah, thanks.
Luc, I have a question myself. In the beginning of the talk, you mentioned other spectral functions like the determinant and heat and so on. Is there anything you would like to say about that is interesting to mention? Or?
Yes. So you can. So it's the okay. It's so I wanted to stress in this talk. I wanted to stress this relation between analytic eigenvalue, analytic eigenbranches, and semiclassical concentration. And so this does not appear if you look at other functions, and this is why I didn't speak. I didn't want to speak too much about it. But for instance, so if you look at Kokotov, so the approach by Kokotov and Korotkin for this, so what they were for these translation surfaces. So for translation surface, so the basic idea is that what you do is you have this moduli space. So on this L shape that I had written, then you can move almost anything as long as you can still pair the corresponding sides together. And so this gives you a certain number of parameters, and these parameters are usually expressed as absolute and relative holonomies, and so etc. And so what you can do is you can use these analytic techniques to compute the derivatives of the eigenvalues in any direction. And so and once you have these of course these derivatives, because you have now a multidimensional parameter space, and analytic perturbation theory only works for one dimension. So they're not good for individual eigenvalue on all the moduli space. But if you're looking at something which is symmetric, then you can derive from this expression for the individual eigenvalue from the Feynman-Hellman formula. derive a variational formula for the spectral determinant, for instance. And so once you have and so what they do is actually they get a system that give them the variation of the log det, and they solve it. They solve it using complex geometry. And so yes, so the first step of this work, you can do it using what I presented today. So when you have you have formulas for the variation of individual eigenvalues, and then if you are able to sum them, then you get variational formulas for log det or for the zeta function or for things like that.
Does anyone else want to say something or ask a question?
Yeah, I had a question about your hyperbolic geometry results. Does this convergence result give you some insight on the present or absence of embedded eigenvalues? Because, for instance, would you know from the fact that there's an eigenvalue some information about the spectrum of these surfaces with the cylinders?
So what I presented, actually, it goes in the other direction. So if you know that these manifolds with cylindrical ends don't have any embedded eigenvalues, then you know something about the possible limits. And so I don't think we can reverse the argument to deduce from this approach the fact that there are no embedded eigenvalues, because actually what I think is that even when there are embedded eigenvalues, actually you cannot construct an eigenbranch that converges to it. So because of these crossings, and it will end up somewhere else. So I don't think you can detect from analytic eigenbranches the existence or it's not easy to detect from analytic eigenbranches the existence of embedded eigenvalue. So what we did with Chris was study so in these hyperbolic triangles with one cusp. So we proved that there were no embedded eigenvalues generically. And this was really where so this last slide is in fact alluding to this proof, and this is exactly the scheme of the proof. So we prove that we first make a change of operator so that embedded eigenvalues become a true eigenvalue. So this is this pseudo Laplacian approach, and then we prove that all the eigenbranches has to go to the lowest threshold, and going to the lowest thresholds means that it is not an embedded eigenvalue. And so and if you want to do it for a surface, then you can do the same. So you take some surface with a cusp, so you modify the condition in the cusp so that you don't have continuous spectrum. But now you want to play with the other parameters. But then you're facing the same kind of problems that I was discussing with Yves. Is that actually our methods work well on triangles, but not on surface, because we have this volume constraint that comes from the genus, and that tells you that you don't have a asymptotic separation of variables directly on surfaces. So right now I don't know how to prove it.
Hugh, anyone else?
May I ask a question? Yes.
Yes, Pavel.
Hello. Can you hear me?
Yes.
So this is concerning your last slide. Yes. So I was thinking about the following. Suppose you have a graph which has a symmetry. Yes. And then you make your model where you make everything stick and so on, preserving this symmetry.
Yes.
And then you can look at eigenfunctions which which are symmetric and then antisymmetric.
Yes.
Then antisymmetric, of course, will converge to another threshold than the symmetric.
Yes.
This crossing view that you are speaking about, they will not.
Yes, yes, you're right. No, yes, you're right. You're right. What I was, my point is that, okay, my statement was not precise enough. My point is that if you have eigenbranches that converge to a higher threshold, then there must be a reason for it.
Yeah, exactly.
So and of course yes, and you're right. You're exactly right. Symmetry is one of these reasons.
One of possible reasons.
One of the possible reasons. The other one is if you have separation of variables, for instance, if you have a complete separation of variables, which is a kind of symmetry too.
Thank you very much. Anyone else wants to comment or ask a question? And if not, let's thank the speaker again. Thank you very much, Luc. Merci beaucoup.
Thank you, Luc.
And we will reconvene next week with a talk by Jake Philman.